现在都到你退休。
你们会不会其实原主是同一个？吴梦是？
没有，我们家都是，而且我看过他的本人跟他的照片。
不像，他瘦瘦小小。
对，因为他来我们办公室的时候呢，我刚好在，因为那时候刚好有舞台转移嘛，然后电视院拿2台人设院，然后就很小一只白白的，然后他的照片是黑白的。
Alright, so we are moving on to lesson 5. This is also chapter 5 in our textbook. In this chapter, we're going to talk about steady-state electric currents. As we progress, you should bear in mind the terminology steady electric current. Is it practical? What are the basic conditions and requirements to maintain a steady current? Okay, you have to think and ask yourselves that question. So in this chapter, I will cover the basic definition of current density, and we will talk about Ohm's law, which everybody here knows. Ohm's law is V equals IR. Right? Voltage is your current multiplied by the resistance. But we're going to look into that in more details. So somehow electromagnetics and electrical circuit will merge. And I want to convince you, basically everything being taught in electric circuit is actually covered by electromagnetics. And then we are going to talk about current laws, Kirchhoff's current law, okay? And then we're going to talk about boundary conditions, and then the method to calculate resistance, right? But anyway, how can you create current? Current, by definition, is you have moving charges, right? Think about it. If you have charge moving in space and time, then you have current, right? So let's come to the blackboard. In the past, starting from high school, I bet each and every one of you already somehow touched current. So current, we like to use I. Capitalized I or non-capitalized I, doesn't matter, but I usually stands for current. And it has the unit of amps. Okay, so we have capitalized A to denote the unit for current. If we decompose amp into the basic units, it is actually coulomb divided by second. All right? So the definition of current is therefore physically how much charges you have flowing in certain time. Okay? And therefore current adopts a unit of coulomb divided coulomb is the number of charge divided by the time duration, seconds. Right? So this is current in the unit of amps. But look at this picture. If you have current flowing, usually currents are actually vectors. Okay, but in the past, we understood currents as a scalar quantity. But now current can actually flow in different directions, right? So the better way to quantify current is we define some vector field, vector quantity called the current density. And then if that current density is making a dot product with some area, and that is equal to the current. All right? So basically, the current density is a vector, right? And it's nothing more than the current divided by the surface area. Surface area. Okay? And therefore, its unit is amp per meter squared. Right? It's just the current density by definition is the amount of current per unit area. Right? So the unit is amp divided by meter squared. But in this PowerPoint, we're also going to introduce current density is actually having the charge density moving at certain velocity. So this rho is something we learned in the past. It's the current density, volume charge density, excuse me. Charge density and multiplied by the velocity. Okay? So you might want to check whether the charge density multiplied by the velocity gives you amps per meter squared. Okay, let's try to do that. So rho has a unit of charge divided by meter cube. Okay, cube, volume charge density. And this mu or u vector is velocity, so it's meter per second. Right? So 1 meter is cancelled out, but you know coulomb divided by second is just amp. Okay, so this is equal to coulomb second and meter squared. So it is indeed amp per meter squared, right? So there are two ways to understand and appreciate current density. One is straightforward, the amount of current divided by your surface area. Another view to understand current density is you have a huge chunk of charges, and therefore you have charge densities, and these charges are moving at certain velocity, thus giving rise to current density. Okay? Now, current densities can be divided into two types depending on how this current is formed. Right? So the first one is called convection current, which is probably no longer in use, but in the past we used convection currents heavily. The second type is conduction current. This is something we use every day until this date, right? So by definition, convection current is something you have the motion of charged particles in vacuum. You don't see this nowadays very often, but if you are an audiophile, you listen to music, especially classical music, a lot of amplifiers like to use this so-called cathode ray tubes, 阴极射线管, right, to produce amplification. The working principle is you have two electrodes. Think of the capacitor, right? You have two conductors. And on one of it, you can apply a very high voltage. The other one is the ground. So you apply a very high voltage, you provide a huge electrical potential. So the positive side is having a very high positive potential, right? And thus, it would tend to attract the electrons out from the bottom electrode, right? So if you have very high positive potential, electrons can be sucked out of the conductor and swing to the positive side, called the anode, right? Now, if you remember, electrons have negative charge, right? So as electrons are sucked out from the bottom electrode, it moves upwards. It is equivalent to a positive charge flowing in the reverse direction. Okay? So electrons flowing from the bottom to the up is equivalent to a positive charge moving from the anode to the cathode. So basically, the current flowing direction is from the top to the bottom. And usually for cathode ray tubes, you need to have a high degree of vacuum, all right? So you can enjoy convection current. So these are the charges really moving in vacuum. In vacuum means there's nothing to block the charges, okay? So this is convection current, but as I mentioned again, I mean, when I was little, the televisions we use are very thick because they are made of cathode ray tubes. But nowadays, you are all using the thin film liquid crystal type of monitors. So you don't really use cathode ray tubes anymore. And that leads us to the second type of current. It's called conduction current or drift current. All right, so conduction current in comparison to convection current, this is a drift motion of charged particles, for example, electrons, and usually in conductors, in metals. Now, these blue big dots are the atoms within certain metal, and these small red circles are used to denote the electrons. Electrons are very light. Okay, they're very light. They are easy to move. So if you apply an external E field, the electrons tends to be moved by the external fields. But the dramatic difference between conduction current and convection current is here the electrons are provided by the metallic atoms. So you have lots and lots of atoms and a lot of electrons. Therefore, as the electrons move under the presence of external field, they tend to bump into each other. Like electrons can bump into another electron, or the atom, the nucleus of the atom tends to be bigger in terms of size, right? So electrons, they move, but they bump into each other or bump into the atoms. But overall, as they move, they bump. Overall, in general, you have a steady flow of electrons from the right to the left. Okay? So the apparent difference for conduction current is you have a drift of the overall motion of the charged particles to a certain direction, but as they move, they bump. Okay? Now, what is the effect of those bumping? Can you just try to understand it in a more physical way? You have a piece of conductor, you apply external field, you create the drift motion of electrons, and therefore you have current. But as the electrons move, they bump into each other or bump into the atomic lattice. Every time they bump, they lose certain energy. Right? And that energy, due to the bumping, is transferred into heat. Okay? And that is called resistance. Right? The higher the resistance means the electrons tend to bump more frequently in that given metal, right? So the drift motion of free electrons undergoes frequent collisions or bumping, right? And therefore you have resistance, right? The next question we have to answer is, why is the drift motion flowing from the right to the left? Well, here we have assumed the externally applied E field direction is from the left to the right. This is, well, the direction the starting point of the arrow means we have higher electric potential or higher voltage. And in the direction of the arrow, you have a reduction in the voltage, right? So this is again conforming to the convection current. Electrons tends to be attracted by the positive potential, okay? So whenever you have positive potential, negative potential, you create the E field from the left to the right, but the electrons are attracted to the positive side of the potential, right? So electrons drift from the right to the left, but again, electrons carry negative charges, right? So equivalently, if you have a lot of negative charged particles flowing from the right to the left, it's equivalent to positive charged particles flowing in the direction of your applied field. Okay? So even in conduction current, the current density produced by the external applied field is parallel to your field. Okay? But in fact, in reality, it's the lighter weighted electrons that's drifting. Alright? So, the drifting velocity of electrons is proportional to your applied field, but in the reverse direction. Okay? Okay, so I'm giving you some table for different materials. These are known. Aluminum, copper, silver, silicon, they all have different drift velocities. So these are tabled by this constant, right? But what we really care about, I mean, these are too tedious. What we like to call materials, if they can have the ability to have conduction current, we like to use a simple parameter called conductivity. And starting from now on, for the entire semester, I'm going to use the Greek letter sigma to denote conductivity, right? So basically, J, the current density, is indeed the charge density multiplied by the drift velocity. But if we understand this drift velocity is just this mobility constant multiplied by your external field, okay? And then we can just say, okay, finally, once we have certain material, the externally applied field would be in the same direction as the current density created. And the magnitude is directly dependent on the conductivity of that given material, right? So if the conductivity for a certain conductor is very high, then it produces a huge current density, right? So carbon nanotube can actually give you huge currents as compared to common metals, right? So these are just explanation of conductivity. And starting from now on, we can just use the sigma constant to describe different materials, right? Now, let's just say in electromagnetics, the way we understand about the current formation and the flow of current is somehow different as what we learned in the past in electric circuits. Okay? In the language of electromagnetics, you have a piece of conductor. Once you apply certain potential difference, you create external field, and then you create the motion of drift electrons And effectively, you create current density. Okay? So you have a piece of conductor, you have applied potential difference, you have therefore applied external field, and you create current density. And up to now, electromagnetics tells you, well, we can formulate and we can quantify the relationships of the resulting current density and your applied field intensity. And that is simply by knowing what type of material you're using. So J equals sigma E. And that's it. That seems very unfamiliar, right? In the past, what we learned about was, in the circuit theory, was V equals IR. Voltage is equal to current multiplied by resistance. Okay? Now think about it. What's the difference between the two? Or eventually they mean the same thing. It's the same language, it's the same sentence, but spoken by two different languages. This is Mandarin Chinese, this is Taiwanese. Now think about it. What is the difference? And this is the page I really want to convince you. If you can master electromagnetics, basically you understand everything in circuit theory, ideally, if you really master electromagnetics. So let's try to prove these two are really the same sentence, but only pronounced in different languages. Okay? So V equals IR. What is V? V is the potential difference. And the potential difference is derived from the line integration of along the direction when you come back or against, you work against E field, right? So if you want to understand about the potential difference between these 2 points, this is 2, this is 1. If I want to understand the potential difference between points 2 and 1, all I have to do is perform integration. The line integration of my differential length and my field. Now you might be puzzled because in the definition of V, we focused on the fact that we need to add a negative sign. Right? I spent a lot of time telling you V is the negative line integration of E dot dl. But how come in here I don't have the negative sign? Can anyone try to answer that by yourselves? This is the point where you have to understand how is this V defined in circuit theory. V equals IR. What does it mean? What does this V stand for? When you move in the direction of the current, you multiply by the device's resistance, you produce a voltage difference, potential difference. But when you have a positive V, what does it mean? Now go back and check your circuit theory textbook. Probably in the first chapter, up front, it will tell you we are working in the passive sign convention, which means if you have a positive V, it means you actually have a potential drop. Okay? So therefore, in order to match circuit theory using passive sign convention, a positive V means you have a voltage drop. Here, we removed the negative sign. Okay? To represent, we actually have a drop in potential, a reduction in potential. Voltage drop. Okay? So as I move from point 1 to point 2 in the direction of the external field or in the direction of my current density, I expect to have potential drop. Okay? Therefore, here, I removed the negative sign. But now I know E is simply J divided by sigma, right? So this is telling you, well, in this simple case, I already know the surface area of my conductor, and that potential drop can be directly related to current multiplied by some constant. I know the length, right, from point 1 to point 2 being L. So everything is known. So the voltage drop is indeed equal to the current multiplied by another constant. So in this simple process, I have already derived the formula for calculating resistance, right? You can just call this as R as compared to the circuit theory. So basically, once you have a conductor, you know its length, you know its surface, you know its area, and you know its conductivity, you know its resistance. Okay? So I'm giving you a very simple, workout problem. You can try to calculate. So usually we use copper to make cables. So if the copper cable is 1 kilometer in length and it's in a circular geometry and the radius is 1 millimeters, try to calculate its resulting resistance if you know the sigma for copper is 5.8 times 10 to the 7th. Now try to do the calculation on your own. Okay. 1 kilometer of copper wire with that radius, probably around 5.5 ohms, extremely small. Okay, it's 1 kilometer in length, but only 5.5 ohms. Okay, try to calculate that. Okay, so now we can move on to the current loss. We know externally applied E field creates current densities in conductors. And now we know how to formulate them. J equals sigma E. So once you know the material's conductivity, you know the current density. How can that really help us? Well, once we know J and E, they're related, we have already derived Ohm's law, V equals IR. And then we can also understand other things, right? KVL, Kirchhoff's voltage law, Kirchhoff's current law. Everything can be understood. And as I promised, if you still remember, in the previous chapter, up front, when we talked about metals, I told you perfect metals cannot have charges inside of it. But if you forcefully inject charges into the metals, the charges will swim to the surface in a very short time. And now is the right moment to prove that statement is true. So we are going to talk about charge dynamics in conductors. Now that we have the basic understanding of conductivity, finally, we have the ability to understand it. All right. Again, just to recap what we covered in the previous subsection, J equals sigma E. So sigma is the conductivity for that conductor. Still, E fields are conserved. So that means you cannot violate curl of E equals to 0, right? E fields, by default, are conserved, so the curl of the E field intensity must be 0, right? And whenever you see this curl equation, curl is related to finding the circulation in a closed loop. So that is transformed, you form a closed loop and you evaluate the resulting closed loop integration of the E field intensity. And that has to be 0. Otherwise, you're working in a non-conserved field. So we can simply replace E by J divided by sigma, right? This is coming from the fact J equals sigma E. So this formula tells us, well, somehow current density, well, divided by sigma. Sigma is a constant. We can just put it out of the line integration, right? So this formula is telling you, well, current density is also a conserved field, right? Now think about it. Does it make physical sense? I mean, this one makes physical sense, right? In the world that we live in, E fields are conserved. But somehow J equals sigma E, so if this is conserved and that's a constant, it's making J also conserved, which is too true. Cannot be wrong. And therefore you see this equation, you accept it. But this is a point where you really have to ask yourselves and cast doubts. How to form steady state electric current in the first place? What do I mean by that? Well, let's take a closer look. So imagine in space you have a positive charge, right, moving with certain velocity, and that gives rise to J. Okay? Now the entire chapter assumes you have a constant and steady flow of charges at a given velocity, right? Therefore you have J. So if you have some kind of circuitry, well, some kind of circuitry. Okay? This is some circuitry, right? We want to form a closed loop. So you might have two resistors connected in series. So think about it. If this is true, J, we can skip sigma, right? Assume sigma is 1. So J dot differential length, we form a closed loop, has to be 0. So let's check. We formed a closed loop called C, right? And the closed loop direction for the top segment from the left to the right, and then it goes down, reverses direction, and also reverses direction in the y direction. Okay? So that is my closed loop C. On the top segment, I have assumed the positive charge particle moves from the left to the right. So my J is moving from the left to the right. Okay? So once the charge moves to here, to this corner, how should it move? I mean, it's simple, right? It's just So my current is moving from the left to the right, and once I hit this corner, it has to change direction. It has to bend by 90 degrees, right? When it reaches to here, current density or the flow of the charge keeps on going, right? And then when you miss this corner, it goes up, right? This is how you maintain a steady state current, right? So this charge moves across the resistor, goes down, moves here, and goes up. And therefore, you have a charged particle continuously moving in this loop, right? So this probably answers how we can maintain a steady flow of charged particles, right? We have to form a closed loop. Otherwise, the particles move, then after some time, you don't have any more particles, right? So once you form a closed loop, this one goes around and comes back here again, can move, right? So the total number of particles does not change, and therefore you have a steady flow of current. If you're smart and if you're sensitive, you can catch some bug in that statement. And you should be able to catch the bug. Because if we want to maintain a steady flow of current, it means this charge has to move with a constant velocity, right? But the fact I have resistance in my circuitry, that means when the charged particle is moving along the loop, it loses energy, right? When it loses energy, its velocity should be reduced, right? It's due to bumping, due to collision. Every time you bump, you lose a small portion of the energy into heat. So even though the number of particles can be maintained in this closed loop, but the velocity cannot be maintained at a fixed rate. Okay? So what's the problem? That's problem number one. The velocity cannot be maintained. And the second one, it seems to violate this universal truth. This equation tells you, in my closed loop circuitry, the line integration of J should be 0. But let's check, okay? That is checked. Here, the top segment, J is in the same direction of my differential length. So this is giving me a positive sign, right? J and DL are in the same direction. So they multiply together, they're positive, it gives you a positive value. Here, again, the current is bended in the same direction as my differential length. So these two multiply together, again, gives me a positive value, right? Once I perform the integration. Here, same direction, positive. Same direction, positive. So you add 4 positive stuff. How can that be 0? This is a challenge to you. Draw a simple circuitry, and you assume to have a steady flow of current. Can you try to prove, or just try to convince me? How can this universal truth be held? it's actually problematic, right? We have two problems. Number one being, well, it seems like the closed loop integration is not equal to 0. And the second one is mu seems to be not a constant. Okay. Such a simple circuitry already violates two of our understandings. Okay? So the fact of this equation being so simple, you must be able to link the equation to reality. So the basic question, or the two problems, can be answered by asking ourselves one simple question. I mean, how can we maintain this circuitry to operate with a constant current? Any answer from the student? No? How many students are watching?
8.
8. Well, anyone that understands about circuitry knows that in order to operate, right, a circuitry, there's no free lunch. If you want to generate current, you have to feed the circuitry, right? If you want your horse to work, you have to feed it grass, right? Okay. So that magical box is called the batteries, or the sources, right? This is something you learned. So in the past, in this box, you have to provide battery in the form of voltage, or you can have the current source. Either way, right? Which means circuitries are not there for free. You have to donate energies to make it operate. And basically, a circuitry gives you functionality, but it always induces losses. Okay, it's fake. So what I want to emphasize is the batteries that you use every day are very weird elements. I mean, they are ideally producing non-conserved fields. Okay. What do I mean? Let's look at the inside of a battery. Okay? So a battery comes with a positive side and a negative side. It still has two conductors. And to our understanding, the positive sides attract positive charges. The negative side attracts negative charges. Okay? So therefore, usually when you have positive charge, you create the field direction pointing from the positive to the negative. Right? And therefore, if you have a positive charged particle, it tends to move in this direction, right? E. But look at the circuitry. Look at the circuitry. I'm using the shorter segment to denote negative, a longer one to denote positive. In a circuitry, if you want to maintain a constant current, you need to supply some kind of potential difference in order to make it work, right? But when the charged particles move along the 3 segment, it loses energy. But when it meets the battery, it actually moves in the direction from the negative side to the positive side. So the positive charge moves, finishing the circuitry, and goes inside the battery. It moves in a reversed direction as compared to our anticipation. In our anticipation, the positive charge moves in the direction from the positive electrode to negative electrode. But when the particle moves into the battery, it actually moves or swims from the negative side to the positive side, and therefore making the battery itself a non-conserved element, right? So the way to appreciate Kirchhoff's voltage law, this is Kirchhoff's voltage law. Right? The way to understand it is, well, in order to maintain the basic operation of a simple circuitry, you need to apply or supply the battery. So in all these circuit elements, you suffer from potential drops. You lose energy. But once the charged particle enters the battery, it is forced to move in the direction reversed to our understanding in order to combat the energy loss. So it gains energy. Right? So basically, when you move in this direction inside the battery, you have potential rise instead of potential drop. Right? So the basic function of this non-conserved field, right, is forcing the charged particle to move from the negative side to the positive side to give additional energy of the particle, and therefore to maintain the velocity of that charge. Right? So, in order to have a steady electric current, you need to have a non-conserved field element. So when you have a positive charged particle moving with some velocity, although it undergoes a lot of potential drops, but all those energy loss is recovered by this battery. So the number of the charge remains constant. The velocity of the charge remains constant throughout. Okay? Very simple operation, and you must know to operate a circuitry, you need to have sources. But you never thought the significance of those sources are actually providing a non-conserved field element. Okay? Otherwise, curl of J seems to be non-zero. Okay? So let's take a rest for 10 minutes. And we have homework number 4, right, already posted. It's due next Wednesday. And we have our examination number 2 coming up on May 18th, on Monday, right? I know some of you might be depressed by your score on your first examination, but just try to keep up your good work and work hard. You will excel, right? Let's take a 10 minutes rest. right? So let's continue to discover steady state electric current. I want to formulate Kirchhoff's current law, right? So let's reinvestigate or revisit the definition of current. Well, current is generated when you have charge movements over a certain time. But now I'm adding a negative sign, and I'm using partial differentiations to reflect the fact once you have charge flowing, then basically the number of charges is reduced. Okay? So this negative sign is taken into consideration if you have charge moving out, then inside the box you have fewer charges, right? So another way to understand current is the rate of change of charges in certain constant value, okay? If the number of charges is reducing, then you have produced current. But now that we know charge, the number of charge is the volume integration of the charge density, right? This is by definition. But we also know that the current is defined as the current density making a surface integration, right? Current density by definition is current per unit area. So this equality is straightforward, and this equality is straightforward. And this is where divergence theorem is very important. We have the vector current density making a closed surface integration that can be transformed into the volume integration of the divergence of J over the volume, right? This is basically divergence theory. I'm free to convert between volume integration of the divergence of the vector field and the surface integration of the vector field itself. Now, by comparing the terms, I have the volume integration, I also have the volume integration, which means the integrands must be equal. So this is telling you divergence of J is equal to the negative change of the charge density. Try to formulate or try to come up with a sentence that you can understand yourselves when looking at this equation. This is telling you if you have the change of the charge density as a function of time, then you would have some flowing of the current densities, right? This change is in time, but this change is in space. Divergence is a net outward flux of your vector field in certain space. Okay? So this is a generalized equation, but now we are concerned only about the steady current. So what does it mean to have a steady current? Under steady current assumption, this rate of change of the charge density has to be 0, right? Since the charge density cannot change as a function of time, we have steady state. And therefore, divergence of J has to be 0 under this assumption. So what does it mean? Let's take a look at the blackboard. I have 3 different circuit elements connected together, forming a node, right? This point is shared by all these 3 elements. If I want to invoke divergence of J equals to 0, well, divergence means the net outward flux of the field. I can form a volume, right? A solid sphere centered at this node. And I evaluate the outward flux of J. And this is telling me the divergence. The net outward flux of the current density has to be 0 for this node. Okay? So it means it's J2, J1, J3, right? They add up to 0. So I'm hoping you might be very moved or motivated because this is something you were forced to accept as Kirchhoff's current law. Kirchhoff's current law tells you for a given node, the total sum of the current has to go to 0. Or another way to understand it, for a given node, the total current coming in is equal to the total current coming out. So up to now, we have proved Kirchhoff's current law. This is coming from the assumption of steady state circuitry. So your divergence J must be 0 because the rate of change of your charge density has to be 0 under steady state. Right? Now, I want to use this more generalized equation to show you about perfect metals. If you still remember, we talked about if we have a piece of perfect metal and we forcefully inject charges into it, over a very short time, all these charges would surface, right? So that the condition of no charge inside the perfect metal can be satisfied. So now we have the tool and we have knowledge to prove it, right? Again, we start from this continuity equation. This is something we derived, right? Divergence J is equal to the negative rate of change in my charge density. And that's called the continuity equation. But J equals to sigma E, right? This is something we also learned. J equals sigma E is the electromagnetic version of Kirchhoff's voltage law, right? So we combine this knowledge, J equals sigma E, but because sigma can be viewed as a constant, so it does not participate in divergence. All right? I have assumed I have a homogeneous piece of matter. So sigma is viewed as a constant. But then divergence of E is equal to rho divided by epsilon. So rho on the right and rho on the left. So this equation contains a lot of knowledge. This is like a basic summary to what you have learned up to now. This is something we learned as continuity equation, and this is Kirchhoff's voltage law in EM language, and this is using Gauss's law. The combination of 3 different knowledges, or knowledge. You cannot count knowledge. Okay? Simple equation contains a lot of knowledge. So this is a very simplified equation. All we have to solve is we move this right to the right. So we are interested in the rate of change of the charge density, right? We inject the charges into the metal. We want to see how it decays, how the charge density is decayed to 0. Because inside the metal, ideally we cannot have charges. And therefore the charge density has to be reduced to 0 over a certain period of time. This simple differential equation can be solved directly. I believe you're all capable of doing it. So basically, the charge density as a function of time is your initial charge value, and then you have exponential decay, right? Exponential decay in that tau is called the time constant. And that time constant is, in this case, is epsilon divided by sigma. Tau is epsilon divided by sigma. So if you go back and check in your textbook for a certain ideal metal, you will find the epsilon value and sigma value, right? You divide them, you find the time constant. And that time constant typically gives you an extremely short duration, 10 to the negative 19th second. Super, super fast. So this corroborates what I showed you previously, right? If you have a good piece of metal, you inject charges into it, within such a short time period, all the charges will be forced to swim to the surface and stay on the surface. And therefore, inside the metal, you still have equal potential and you have no charge density. Okay? So try to appreciate these three equations, cascaded together, but combining a lot of the three different equations, laws, into a single equation. Right? Okay, so now let's investigate into boundary conditions. Why do we care about boundary conditions? Well, in reality, you might have different layers, different materials connected together. So if you only know the field or the current value in one medium, through boundary condition, we know the field and current values in all other medium. Okay? So let's revisit what we have covered up to now. Current density, J, is a vector. Under the steady state condition, divergence of J has to be 0. This is under steady state. So this is expressed in a differential form, but in integral form, we have a closed surface integration of J has to be 0. This is Kirchhoff's current law. On the other hand, curl of E remains to be 0, right? E fields are conserved. So J equals sigma E. So we have the curl of J divided by sigma has to be 0. Expressed in the integral form, in a closed loop integration of J divided by sigma has to be 0. So looking at these four equations and ask yourselves, whenever we think of boundary, we have two different materials, right? We have medium 1, medium 2. Well, whenever we have two different materials, we form an interface. So the boundary conditions are no more than, well, if we know the field or current in one medium with its magnitude and angle, we want to know what is happening in the second medium. You need to have this capability now. Divergence condition or divergence equation always tell you how the normal components across the two interfaces are related. Curl condition always tell you how the tangential components are related across the interface. Okay? So the tangential component, due to curl of J divided by sigma equals to 0, so the tangential part has to be the same. So therefore, the tangential part in the first medium of the current density divided by the first medium's conductivity has to be equal to J2T divided by sigma 2. Curl relation always tell you how the tangential parts are related, okay? Because you have to form a closed loop. The normal component is always taken care of by the divergence formulation. So J1n is equal to J2n. Okay? So we take a look at one example. We have two conductors. The top one is having sigma 1, the bottom one is having sigma 2. If I know I injected certain current density from the first medium into the second medium, so basically J1, the magnitude of J1 and the angle with respect to the surface normal is known. So alpha 1 is known, J1 magnitude is known. Can I deduce the magnitude and angle in the second medium? And that's the benefit of using boundary conditions. First one, tangential part of the E field remains the same, which means J1 times sine alpha means J1t divided by sigma 1 has to be equal to J2t, right? This one, J2t divided by sigma 2. Now, this first equation is telling you nothing more than curl of E equals to 0. But I want to train you in a different way. Look at the figure and take a guess. Which material is having a larger conductivity? Can you know it just by looking at the figure? Currently, J1t is shorter, right? J1t is shorter than J2t. So what does that tell you? It tells you sigma 2 has to be greater than sigma 1, right? Because J2t, a longer J2t has to be divided by a larger sigma 2 in order to be equal to a shorter J1t divided by a smaller sigma 1, okay? So for you, you have to understand it. If a material is having a larger conductivity, it can produce a larger tangential component in its current density, and thus making the angle larger. Okay? So this is a training for you. If sigma goes up, alpha goes up, J_T goes up. Okay? This is some capability that I want you to have. Try to summarize your own knowledge using your own word after the vast amount of part points and derivations. And then you carry it for the rest of your life. Okay, I know it's very difficult, but that's my anticipation. Okay, so took care of the tangential part, and now J1n is equal to J2n. So that's a cosine part. Okay? Again, like the dielectrics, we divide the two equations, we find the angle. Remember, alpha 1 is given. So now alpha 2 can be deduced directly. Now that we know the angle, we can find out J2 amplitude, right? J2 amplitude is just the summation of the normal component and the tangential component squared, and then we take the square root. Okay? So this is basically mathematics. The key issue is, are you able to understand from these two basic equations, divergence of J equals to 0 under steady state current condition? And then you know, oh, this is actually telling me if I have an interface formed by two different materials, then the normal component must be continuous. And this curl equation tells me how tangential components must be related. Okay? By now, you must have this capability. Curl equations always tells you the tangential components. Divergence always gives you the normal components, how they are related. Okay? So if we have two conductors, things are quite easy, straightforward. What happens if, well, this is a very unique case. Again, we have two materials forming an interface. Okay? But what happens if in this case, these are conducting dielectrics? What does that mean? Conducting dielectrics. Ideally, dielectrics are non-conducting, right? So these are bad dielectrics. These are dielectrics that actually permit to have some kind of flow of charge, okay, in the form of conduction current, right? So for these materials, we need to use epsilon and sigma to describe it. So usually, I mean, for pure conductors, we only want to have sigma. But here, they're imperfect dielectrics or imperfect conductors. We need to use both epsilon and sigma to describe it, right? So the first material, epsilon 1, sigma 1. Second material, epsilon 2, sigma 2. Now, let's try to investigate into this unique case. All right, so we want to understand about the current density, and we want to understand about the flux density. Now, remember, well, examination 2 is coming up. So whenever we talk about flux density across two different materials, usually divergence of D is equal to rho free. So remember, there might be charge densities deposited along the interface. If you don't draw this surface charge density, then you're not looking at the picture right. Okay? So this is a particular case where you have current flowing across the interface, but at the same time, you might have charges being deposited over the interface. Okay? So let's try to unveil the secret. In this case, if I have the tangential part of the current density, they must be equal. Each has to be divided by its corresponding conductivity. This is just the same. as our previous boundary condition, right? And this is also telling you tangential component of the E field intensity across the two materials must be equal. Normal component, nothing more, J1n equals J2n, right? Nothing more. But what is new here is for this imperfect dielectrics, D1n minus D2n equals rho s. This is something we covered, right? So in the normal direction, we have to take account into two facts. Even though you have a steady and equal amount of current density, you actually might have accumulation of charges on the interface. So this one, J equals to sigma E. So the normal component in the current density are equal can be reformulated into sigma 1 E1 normal component is equal to sigma 2 E2 normal component, right? And D equals to epsilon E, so D1n is now reformulated as epsilon 1 times E1n and minus D2n is equal to rho s. So as you can see, in the tangential direction, there's no story about the tangential component. But the normal component is quite exciting and quite complicated, right? We have two equations which needs to be solved simultaneously. The first one is telling me the current density. The second one is telling me surface charge density. So I can actually use the first equation to relate E1n and E2n, right? And then replace into the E1n or E2n in the second equation, and that's what I did. So basically, I want to know how to quantify the surface charge density at the interface, right? I can formulate rho s in two ways, right? In represented by E1 normal or E2 normal, it doesn't matter. What I do care about is looking at this result, or let's move on. I reformulated this rho s for you. So across the interface, you always have the normal E field intensity, right? Well, either you describe rho s in the form of E1n or E2n, does not matter, but look at this two within the parentheses. E1n is non-zero, rho s is something we want to investigate, but epsilon 1 minus epsilon 2 and multiplied by sigma 1 divided by sigma 2. So my first question to you is, if you have two imperfect dielectrics that both can have conduction currents, when do we anticipate to have no surface charge density? Well, rho s to be 0 can be satisfied both by these conditions equal to 0, right? So which means epsilon 1 is equal to this amount, or this amount equals to that, the same, right? So think about it. When can there be no surface charge density? Rho s can be 0 only if, well, only if this one goes to 0, right? When this one goes to 0, you actually have a very particular ratio of the material conductivity to the permittivity. So for both material, you have to have the ratio of conductivity 1 to permittivity 1 equaling conductivity of material 2 to permittivity of material 2. Now think about it. I mean, what are the chances for you to have this happening? And magically, you just chose two materials and they obey this relationship. It's almost impossible, right? I mean, gold and silver, I mean, you expect this relationship to hold? Probably not, okay? So as a summary, whenever you have imperfect or leaky dielectrics, so the dielectrics, they actually do carry current, you always expect to see resulting surface charge density. The magical case is this ratios hold, then you have no surface charge density, but that's too rare. It's almost impossible. But the second possibility is when both materials are non-conductive, right? Think about it. Initially, we assume these two are imperfect dielectrics, so we allow to have conduction currents. Because of conduction current, and even though sigma 1 does not equal to sigma 2, but divergence J equals to 0, it forces you to have a constant and continuous flow of current in the normal direction. In order to meet that, some remaining charges from this one must be held as a prisoner at the interface. It cannot flow across, right? And therefore you have surface charge density. It's due to the mismatch between sigma 1 and sigma 2. But now everything will be relaxed if the two materials are perfect dielectrics. Perfect dielectrics, you don't have sigma 1, you don't have sigma 2, and you don't have J. So in that case, you don't have the surface charge density. So in the case where both sigma 1 and sigma 2 are 0, you have perfect insulators, non-conductive, you don't have surface charge density. Okay? So we can actually learn a lot from the understanding of boundary conditions, right? I want to show you a practical case. Well, we come back to the parallel plate capacitor. In the past, we somehow filled the capacitor with perfect dielectrics. But sometimes, I mean, in the real world, dielectrics tend to be slightly conductive. Okay, cannot be blamed. So what happens if this given capacitor is filled with two different conductive dielectrics? All that we know is the surface area of the plate is S, and we apply a potential difference of V. And we know the material properties. We know epsilon 1, sigma 1, epsilon 2, sigma 2. Then, are we capable of finding J, the current density, in the two materials, and E field intensity in the two materials? And is it possible that we actually find out the resulting charge densities? remember, charge densities, I'm using plural. In this particular geometry or system, how many charge densities do you have? Well, you have the metal dielectric interface. As long as you have interface, you might have surface charge density. So you have surface charge density 1, surface charge density 2, and these are both metal dielectric interfaces. Easy to solve. But now you also have a third interface. This is across two leaky dielectrics, right? So remember, whenever you meet this type of problem, you have 3 different surface charge densities to be solved. But let's nail it one by one. We want to determine the current density, the field intensity, and charge densities. How should we start? Well, we know from boundary condition, J normal are continuous, right? And in this case, again, we can assume the 2 parallel plates are quite big as compared to the total distance. So all the E fields and all the current densities are flowing in the normal direction. So we don't have the tangential components, right? So J1n is equal to J2n. So basically J1n equals to J2n means the entire current is flowing smoothly, only in the normal direction, okay? So both J1n and J2n are equal. I have a constant current. So constant current multiplied by R1 plus R2. What is R1, R2? The resistance for the first material. R2, the resistance of my second material. Today, we already introduced how to properly formulate the resistance. Once we know the length, we know the area, we know the conductivity, we know resistance, right? So we can directly write down I times R1 plus R2, and that is equal to my supplied potential or voltage. But J is nothing more than current divided by the surface area. So this is straightforward. For this given problem, right? Parallel plate, very big plates. You can just calculate the current density. Second, well, if you were asked to find the E field inside the materials, what you know is, well, E1 and E2 can be different, but basically they're all directed in a normal direction. But once you perform the line integration of E1 over D1 plus E2 times D2, the total potential comes up to V, right? So V has to be equal to E1 D1 plus E2 D2. Okay. Where is this coming from? This is actually coming from J, okay? Because divergence of J is equal to 0 and J equals to sigma E, you know that sigma 1 times E1 is equal to sigma 2 E2, okay? So somehow we can reformulate here E1, E2 using from the help of this equation. So you have 2 ways to formulate it, right? You can express E2 as sigma 1 divided by sigma 2 times E1, which is this case. Or you can replace E1 by moving this downwards. Okay, so you have 2 ways to express it. that's what you have. Voltage is given, right? Voltage is given, so you can quickly derive the results for E1 and E2. But the problem comes for the charge densities. Again, as I emphasized, we have 3 interfaces. So you have to properly formulate or evaluate all surface charge densities. Now the first one is quite straightforward. I mean, rho 1 is the surface charge density across the top metal dielectric interface is directly given by epsilon 1 E1. If you have problem knowing why rho 1 is equal to this one, this is really the time for you to go back to the boundary condition for E fields. Why can't I just write down this? D1n minus D2n equals to rho, but because now I have the top material being metal, I assumed these metal plates are comprised of perfect metals. So inside the metal, you cannot have fields. Okay? All right? Rho 2 has to have a negative sign. Why? D1n minus D2n equals to rho, but now the bottom is now replaced by metal, so D1 is 0. Therefore, you have a negative sign. And this has to be negative, right? So if you add the two together, you might have charge cancellation, and you have to maintain charge neutrality. Okay? So these two simple formulas actually test your understanding to use D1n minus D2n equals rho S. Okay? For the top interface, D1 is in the dielectric and D2 is in the metal, so this one is 0, so you have positive charge. But for the bottom surface, bottom interface to the top, this is dielectric and this is metal, equals to 0. For the bottom, you have metal, but you have no field inside, and you have the dielectric, so you have the negative sign. Okay? And the physical meaning is the top and bottom charge densities need to have different signs to preserve charge neutrality. Okay? All right. At this point, do we need to calculate this rho? The surface charge density across the two conducting dielectrics. Well, of course, I mean, you can calculate it, right? D2 minus D1 dot the surface normal, that gives you the surface charge. But if you calculate in this way, you are following the basic formula, which is fine, But is there a quicker way to do this? There's nothing wrong when you invoke this basic equation, right? There's nothing wrong. The difference of the two flux densities making a dot product to the surface normal gives you the right amount of charge density, which is fine. You already know E1n, E2n, so you know everything. But is there a quicker way? Why am I asking this? Can you tell me, does rho 1 plus rho 2 equals to 0? Let us come back to the simplified version of the problem. Let's come back to the two parallel plates. If the two parallel plates are filled with only one material, let's call it rho 1 and rho 2. Okay. If the parallel plate capacitor is filled with a single material, rho 1 plus rho 2 equals to what? Can any student watching the streaming tell me this answer? No one? I'm going to give you a choice. 0, not 0. Number 1, number 2. I mean, the filming crew and the TA can also raise your hand. Choosing 0, raise your hand. No hands. Not equal to 0, raise your hand. And still no hand. That's a typical problem for Asian students. They just ignore the question. Think about it. We emphasized about charge neutrality, right? So the total number of charge needs to be maintained at 0 because you don't create charges magically. So this means when the parallel capacitor is filled with only one material, on the top interface and the bottom interface, they share the same strength of E field. Okay? And thus, rho 1 and rho 2 has to be equal in amplitude but opposite in sign. Right? If you have positive 5 coulomb, you have to have negative 5 coulomb so that totally there's no charge. And that's called charge neutrality. But now that the fact this capacitor is filled in this way, right? Top you have material 1, bottom you have material 2, and thus making your E1 and E2 being non-equal. And therefore your D1n and D2n non-equal, right? So basically, rho 1 plus rho 2 does not vanish to 0. Okay? So if you have this filling, epsilon 2, epsilon 1, when you have two different fillings, I mean, rho 1 plus rho 2 will be not equal to 0. But charge neutrality still needs to be maintained. So that means you have rho Si. So rho Si is equal to rho 1 plus rho 2, probably in a negative sense. This is a quick and straightforward way to calculate rho Si. Of course, you can invoke this, conventional equation to calculate based on the fact E1 and E2 are different. But what I'm saying is, charge neutrality cannot be violated. So, rho 1 plus rho 2 plus your internal surface charge density still needs to be 0. Right? So once you can quickly formulate rho 1 and rho 2, rho 1 and rho 2 plus rho 1 plus rho 2 and take a negative sign, that is your internal surface charge density. And there is more deeper implication. What does that mean? What does that mean? Why charge neutrality has to be maintained? Let's try to relate to Gauss's law. Gauss's law tells me, well, if I form a closed surface, so if I am someone standing outside of capacitor, right? Divergence of D is equal to rho free. So if I'm standing outside, I have a closed surface encompassing the capacitor, so I'm outside. Charge neutrality tells me rho 1 plus rho 2 plus this internal surface charge density is always equal to 0, right? Due to this fact. So this is 0, meaning when I'm outside of the capacitor, there's no E field. Right? We assume this parallel capacitor is huge, so all the fields are self-contained between the two plates. And therefore, when you're outside, you don't have field lines. You don't have field lines in the language of Gauss's law is when you're outside and you look inside. All the charges adding up inside the device has to be 0. There's no net charge. Okay? So that is actually a beautiful manifestation of Gauss's law. Right? So you have a quicker way to find rho S1. Alright, stop here, and we will come back on Wednesday. But on Wednesday, I will quickly sum up the electric current, and we will move into magnetics. Exciting topic. Alright, see you on Wednesday.